For years, astronomers believed they had found the master key to the cosmos, a model so accurate, so powerful, it seemed unbreakable. It was called Lambda CDM. This model explained how the universe formed, how galaxies grew, and what invisible forces shaped reality. It wasn't just theory, it was the foundation of modern cosmology. But in 2024 and 2025, something changed. One of the first tremors came from the James Webb Space Telescope. It peered deeper into space than ever before, and what it found didn't match the script. Galaxies that were too massive, too bright, too early. Formations that weren't supposed to exist for another billion years. Behind the scenes, scientists were stunned. One researcher admitted, "I couldn't sleep for days. It felt like everything we believed was wrong." Across papers and conferences, the same words echoed: surprising, anomalous, impossible. The universe was speaking, and its message was clear. You don't know me as well as you think. In this documentary, we'll explore the quiet revolution unfolding in astronomy. Because when your most trusted map starts failing, you only have two choices: patch it or throw it out. Gaia BH3, the impossible neighbor. In early 2024, the European Space Agency's Gaia Space Telescope made a discovery that sent shockwaves through the astronomical community. Just 2,000 light-years from Earth, practically next door in cosmic terms, it identified a black hole named Gaia BH3. But this wasn't just another dark object cataloged among thousands. With a mass 33 times greater than our Sun, Gaia BH3 instantly earned a historic title: the most massive stellar origin black hole ever discovered in the Milky Way. Yet it wasn't the size alone that stunned scientists. What truly rattled them was how deeply this black hole challenged everything we thought we knew about how such giants form. According to decades of theory, black holes of this scale should only emerge in the early universe, in regions with extremely low metallicity. That's because heavy elements, what astronomers call metals, like iron, shorten a star's lifespan and prevent the kind of massive core collapse needed to birth something like Gaia BH3. In metal-rich areas like our corner of the galaxy, such a black hole simply shouldn't be able to form. And yet, here it is. Gaia BH3 lives in a metal-rich region, calmly drifting through space like a ghost. No swirling accretion disk, no X-ray flares, no dramatic gravitational outbursts, just silence. Its presence wasn't announced. It was inferred quietly. As one astronomer put it, it's like walking outside and seeing a dinosaur drinking from your garden hose. That moment forces a deeper question. Could it be that our models of stellar death and black hole formation are incomplete? Or, even more bizarre, is it possible that Gaia BH3 formed in the early universe and somehow migrated here over billions of years, slipping unnoticed into our celestial neighborhood? Either way, Gaia BH3 reminds us of a crucial truth. Space doesn't only hide its mysteries in distant galaxies. Sometimes the strangest revelations are right in front of us, like the hidden water beneath Mars's surface or the quiet anomalies in familiar skies. The universe proves again and again that we still have no idea what might be lurking just beyond our reach. Because in the cosmos, the most unexpected wonders are often the ones closest to home. 2024 TVD, A Black Hole Far From Home. On May 8, 2025, NASA's Chandra X-ray Observatory and the Hubble Space Telescope witnessed something truly extraordinary, an event designated AT 2024 TVD. A massive black hole tore a star apart in a violent tidal disruption. But what made this event remarkable wasn't just the destruction, it was where it happened. At 2024, TVD took place 2,600 light-years away from the center of its host galaxy, a galaxy located nearly 600 million light-years from Earth. And that detail changes everything. Normally, tidal disruption events, where stars get shredded by black holes, occur at the heart of galaxies, near supermassive black holes embedded deep in galactic cores. But this one happened far from any center, in a region that shouldn't host such a colossal force. This unexpected location suggests something radical. There may be a second massive black hole lurking in the outskirts of that galaxy. And not just any black hole, Early estimates suggest it's roughly 1,000,000 times the mass of our Sun. Such an object shouldn't be there, unless perhaps it was thrown there. One theory, known as three-body interaction, offers an explanation. When two supermassive black holes interact, often during galactic mergers, one can be gravitationally slingshotted out of the core, ejected into the galaxy's outer regions. A T-2024 TVD could be direct evidence of such a cosmic eviction. This event challenges the very foundation of how we think galaxies are structured. Traditionally, we imagine a single supermassive black hole sitting calmly at the center, with everything else revolving around it. But a T-2024 TVD hints at a messier reality, one where massive black holes roam far from galactic centers, drifting through space like silent predators. And they're not just passengers. Wandering black holes could actively shape star formation, disrupt galactic dynamics, and rewrite the story of how galaxies grow and evolve. If they're more common than we thought, our cosmic maps aren't just incomplete. They might be fundamentally flawed. A T-2024 TVD reminds us that the universe is not a neat, ordered system. It's wild, unpredictable, and still full of monsters we haven't yet found. Unexpected beginnings. In 2025, astrophysicist Daniel Wan and his team released a study that sent shockwaves through the scientific community, a discovery that could rewrite everything we thought we knew about the early universe. Using advanced simulations, they found evidence that planet formation may have begun far earlier than anyone imagined. According to their models, the building blocks of rocky planets, known as protoplanetary disks, could have emerged just 200 million years after the Big Bang. That's not just early, that's infancy. If Wan's findings are correct, it means that solid planetary surfaces capable of harboring water, and possibly life, may have been forming when the universe was still in its cosmic cradle. The implications are staggering. Until now, the prevailing belief was that rocky planets couldn't form until several generations of stars had lived and died, spreading heavy elements like carbon, oxygen, and iron throughout the cosmos. These elements are essential for forming solid surfaces and ultimately for life. But Wan's team suggests that even the ashes of the very first stars might have been enough to kickstart planet formation. In other words, habitable worlds may have emerged almost as soon as stars themselves began to burn. And that brings us to an unsettling possibility. Maybe life in the universe didn't wait billions of years to appear. Maybe it began almost immediately. If that's true, then maybe we're the latecomers. Perhaps we're just a footnote in a much older, far-reaching story. And Wan's team isn't alone in this revelation. A galaxy named JDS Z14, observed just 300 million years after the Big Bang, was found to be rich in oxygen, a sign that massive stars had already formed, burned through their fuel, and exploded in supernovae. Another early galaxy, MOM Z14, displays unexpectedly bright and complex structures less than 500 million years into the universe's timeline. These findings suggest that the early universe wasn't a slow, quiet buildup. It was a cosmic fireworks show. Stars formed and died in rapid cycles. Galaxies grew at breakneck speed, and planets may have formed in the wake of this chaos. But according to the Lambda CDM model, our current best theory of cosmology, this level of activity simply shouldn't have been possible so soon. Together, these discoveries are forcing scientists to rethink the physical processes that shaped the early universe. Perhaps the cosmos stood up and started walking far sooner than we expected. And maybe life walked right alongside it. Oxygen and the red dots. The James Webb Space Telescope has peered deeper into time than any instrument before it, and what it found has left scientists astonished. One of its most stunning discoveries was a galaxy known as JADES-GSZ14, formed just 300 million years after the Big Bang. But what truly shocked astronomers wasn't its age. It was its chemical complexity. This ancient galaxy contained an abundance of oxygen, a heavy element that can only be forged in the hearts of stars and released into space through their explosive deaths. This meant something profound. At least one generation of stars had already lived and died, just 300 million years into the universe's life. Star formation and death, it seems, began much earlier and proceeded much faster than we ever imagined. The implications are enormous. If oxygen was already present this early, it means that chemical evolution, the process by which simple atoms transform into complex molecules, was underway far sooner than expected. Molecules critical to life may have started forming in the very first billion years of the universe. The potential for life just expanded. But Jade's GSZ-14 was only the beginning. In its first images, James Webb revealed hundreds of strange, glowing red specks scattered across deep space. Astronomers called them little red dots. They were small, just 150 to 500 light-years across, but incredibly bright. Most appeared around 600 million years after the Big Bang, and then, mysteriously, vanished. They don't look like ordinary galaxies. Some may harbor massive black holes, but they don't shine like quasars. They emit no X-rays, and if they were merely ultra-bright star clusters, they shouldn't be this common. And yet, there they are, and no one really knows what they are. Some researchers believe these little red dots may be obscured quasars, active black holes shrouded in such dense clouds of gas and dust that their radiation can't escape. That would explain the missing X-rays. But it still doesn't explain why there are so many of them, or why they disappear so quickly. Their existence points to a much more chaotic and complex early universe than we ever expected. And the mysteries don't end there. In another part of the cosmos, James Webb detected Lyman alpha radiation from a galaxy called JADESGS-Z131. Under normal conditions, this specific light should be absorbed by the thick neutral hydrogen that filled the early universe. It shouldn't be visible, and yet it is. This challenges what we thought we knew about the epoch of reionization, the era when the universe first became transparent to light. For years, scientists believed this transition was gradual and smooth. But now, a different picture is emerging. Perhaps the universe became transparent in patches, lit up suddenly by powerful stars or early black holes, only to fade again into darkness. Together, these discoveries paint a radically new portrait of the early cosmos, one not of gentle evolution, but of intense energy, rapid change, and profound mystery. The early universe, it turns out, was far more alive and far more puzzling than we ever imagined. Giants too soon. Once again, the James Webb Space Telescope has upended what we thought we knew about the cosmos. Its latest observations have revealed something deeply unexpected, a surprising abundance of massive, luminous galaxies in the early universe, far more than anyone predicted. And not only are there more of them, they also appeared much earlier than our models allow. Take MOMZ-14, for example, a galaxy observed just 280 million years after the Big Bang. In theory, galaxies from this era should be dim, scattered, and only beginning to form. But MOMZ-14 wasn't faint or fragile. It was bright, massive, and highly evolved. A cosmic heavyweight in a time when the universe was barely out of infancy. According to the standard models, galaxies simply shouldn't be able to reach that level of complexity so quickly. They would need billions of years of star formation, mergers, and gravitational evolution. But Webb's data is telling a different story. Across the board, the telescope is spotting large, complex galactic structures within the first 500 million years of the universe, a period once believed to be slow, quiet, and formative. These findings force us to rethink the speed at which stars ignite, galaxies merge, and matter organizes itself into the grand cosmic architecture we see today. And it's not just fascinating, it's deeply unsettling for cosmologists. Because our standard model, the lambda-c/d/m model, can't fully account for what we're seeing. The sheer number and brightness of these early galaxies pose a direct challenge to the foundational assumptions of modern cosmology. That's why some scientists are now turning to a bold new idea: early dark energy. According to this theory, the universe might have gone through a different phase of expansion shortly after the Big Bang, driven by a form of dark energy that behaved differently than it does today. This early burst of acceleration could explain how galaxies grew so quickly, so soon. Even more intriguing, early dark energy might also help resolve another cosmic puzzle: the Hubble tension, a growing discrepancy between how fast the universe appears to be expanding now and how fast it should be expanding based on early measurements. Two problems, ancient galaxies and the Hubble constant, may in fact be two sides of the same cosmic coin. Together, these clues suggest something profound. The nature of the universe and the forces shaping it might be far more complex than we ever imagined. Dark energy, once thought to be static and unchanging, may be dynamic, evolving over time, influencing the very structure and fate of the cosmos. These aren't just observations of distant galaxies. They're questions about the fundamental blueprint of the universe, about how it began, how it grows, and what hidden forces might be driving its evolution. The James Webb Space Telescope isn't just peering into the past, it's forcing us to rewrite the story of everything.